On January 17, 2013, an American warship slammed into the Tubbataha Reef's natural park. The United States ship Guardian was a specialized mine countermeasures vessel. It displaced roughly 1,300 tons at full load. It measured about 224 feet in length. The location was a highly protected marine sanctuary in the Sulu Sea. The ship was stranded directly on top of a fragile, living ecosystem. The Guardian was not built like a conventional surface combatant. Standard warships use heavy steel construction to withstand direct impact. This vessel was designed specifically to hunt and neutralize magnetic sea mines. To reduce the magnetic signature that could trigger influence mines, the hull was built from wood and covered in glass-reinforced plastic. That composite design helped the ship operate with a very low magnetic profile in mine warfare environments. It also meant the structural envelope was highly vulnerable to blunt force physical trauma. When a steel hull grounds, salvage engineers may consider tug-assisted refloating, if the hull, the seabed, the tide, and the environmental risk all permit it. Heavy towing hawsers can be passed to the casualty, and the ship may be pulled along the safest available track, often with the goal of avoiding any new sweep across the reef. Even then, the movement is not treated as harmless. It is a controlled compromise because every foot of hull movement can translate into new contact with the bottom. In many groundings, speed matters because weather can turn a stranded ship into a breaking wreck. But speed is never the only objective. Salvage masters have to balance the urgency of removal against crew safety, pollution control, hull condition, and the damage that the recovery itself might cause. For the Guardian, the standard rapid extraction sequence was immediately vetoed. The surrounding Tubbataha Reef was a globally recognized living monument, and pulling a breached 1,040-ton mass across a living coral shelf would have turned the hull into an industrial plow. The United States Navy assessed the hard physics of the site and determined that traditional drag-based salvage was incompatible with the survival of the reef. The ecological stakes superseded the recovery of the hull intact, leaving salvage commanders with a massive industrial weight that could not be pulled backward under any circumstances. The grounding now turned that design choice into a load problem. The reef provided an unyielding, highly uneven foundation, and the vessel's weight was no longer supported by uniform hydrostatic pressure. Instead, the 1,040-ton mass rested unevenly on isolated points of hard coral. That boundary left the emergency salvage team with a deteriorating asset in a highly exposed, isolated position. The winter monsoon now controlled the timeline, turning a pinned wooden geometry into a breaking load problem. Heavy atmospheric systems generated continuous, towering swells across the open waters. These sustained weather patterns drove massive walls of kinetic energy directly into the stranded vessel. The resulting wave action introduced a lethal physical cycle to the exposed salvage site. The ocean surface constantly rose and fell, refusing to let the heavy hull rest statically on the hard coral foundation. The incoming weather essentially weaponized the surrounding sea. The destructive mechanism was hydraulic. As each large swell approached the shallows, rising water generated localized buoyancy and lifted the stranded mass slightly off its jagged resting point. As the wave crest passed and the water level dropped rapidly into the following trough, the temporary buoyancy vanished instantly. Gravity slammed the entire weight of the vessel violently back down onto the hardened coral structures. This brutal vertical cycle repeated continuously, minute after minute, hour after hour, driven by the uncompromising winter weather. The wooden frame and glass-reinforced plastic sheathing had little resistance to repeated abrasion against coral. The outer, reinforced plastic layers were quickly shredded by friction against the unyielding coral heads, peeling away in long, torn sections. Once the protective exterior coating was stripped away, the raw wooden timbers were fully exposed to the unrelenting mechanical grinding action. The hard coral became the fixed, striking surface beneath the wave cycle. The ship was repeatedly driven onto the uneven points of the biological shelf, concentrating extreme localized force onto very small surface areas. The sustained kinetic impacts localized immense mechanical stress along the fragile wooden keel. The organic internal framing began to snap under the relentless vertical trauma. The ocean was actively dismantling the ship from the bottom up. That grinding soon became perforation. The reef was not a flat surface, but a jagged field of limestone peaks and biological crevices. With each impact, hard coral punched through the wooden planking until the bottom opened from beneath. The keel damage and repeated perforations collapsed the ship's remaining structural integrity. Seawater moved through the broken bottom into multiple compartments, eroding any realistic hope that the minehunter could regain stable buoyancy as an intact ship. It was no longer a salvageable hull, but a wreck breaking apart in place. The rapid disintegration of the physical hull severely accelerated the emergency operational timeline. The continuous environmental impacts threatened to rip the remaining internal machinery spaces wide open. Deep within the shattered wooden framing, storage systems remained vulnerable to the incoming wave strikes. With the lower hull utterly destroyed, how do salvage teams prevent thousands of gallons of toxic liquid from poisoning the sanctuary? Deep within the shattered lower compartments sat the secondary threat. Approximately 15,000 gallons of marine diesel fuel remained secured in the internal bunker tanks. If wave action breached those storage spaces, diesel could spread through sensitive coral habitat and turn the grounding from a mechanical injury into a chemical emergency. The emergency response shifted into strict containment. Salvage commanders initiated defueling, making the total extraction of liquid contaminants the mandatory prerequisite for any dismantling or heavy lifting. The logic was simple. If a heavy component shifted later, a dry hull would drop broken wood into the water. A wet hull could unleash an environmental disaster. Operating deep inside the wrecked minehunter presented immense physical challenges. The vessel rested at an awkward, unnatural angle on the uneven marine shelf. The lower decks were entirely flooded with raw seawater rushing through the shattered hull bottom. The ship had lost all internal electrical power, plunging the interior compartments into total darkness. Salvage personnel had to navigate manually through a chaotic, dangerous labyrinth of fractured wooden timbers, hanging debris, and displaced mechanical systems. They operated in wet and highly unstable internal spaces while the ocean continued to batter the exterior shell of the vessel. The crews meticulously rigged specialized fluid transfer equipment from external salvage vessels. They established secure, reinforced hose lines running from the deep internal bunker tanks all the way up through the narrow hatches to the exposed weather decks. Every single connection required intense scrutiny and manual verification. The engineering discipline had to be flawless. A single loose coupling, a minor hose rupture, or a momentary loss of pumping control would release the toxic marine diesel directly into the pristine ocean environment. The physical transfer system had to maintain total integrity despite the constant movement and vibration of the dying ship. Pumping operations commenced under intense, continuous observation. The salvage teams carefully managed the fluid dynamics, drawing the heavy fuel up from the lower hull against gravity. They monitored the pressure differentials closely to prevent any sudden blowouts or leaks within the temporary transfer lines. Moving heavy liquid mass out of a structurally compromised vessel also inherently changes its internal weight distribution. The engineers required constant reassessment of the physical stability of the wreck as the heavy fluid was displaced. The crews executed the extraction process methodically, balancing the urgent speed of the collapsing time window with the absolute requirement for total environmental safety. The transfer sequence achieved its critical goal. The teams removed the approximately 15,000 gallons of diesel fuel from the ship's tanks during controlled defueling operations, and other recoverable hazards, including petroleum-based products and wastewater, were removed as far as practical while the wreck continued to deteriorate. No fuel leak was reported during the defueling phase, sharply reducing the risk of a major pollution event on the protected reef. With the chemical hazard neutralized, the emergency narrowed to a physical engineering problem. The ruined wooden mass still rested heavily on the fragile biological shelf. Toxic liquids are gone, but how do you remove a wrecked ship that is too fragile to tow and too heavy to lift? With the fuel removed, Salvage Command shifted to the only viable extraction strategy. The ship was too fragile to drag and too massive to lift intact, so the Navy authorized complete dismantling in place. The recovery would no longer try to save the hull. It would convert the wreck into liftable sections without sweeping it across the coral. This decision initiated the rigorous engineering process of in situ sectioning. Rather than attempting to patch and reinforce the shattered structure, engineers systematically mapped the hull to divide it into manageable vertical blocks. The operational objective was to sever the longitudinal strength of the ship deliberately from the top deck down to the keel. By cutting downward through the main decks, transverse bulkheads, and the heavy bottom timbers, they could isolate massive chunks of the vessel. This method bypassed the impossible requirement of a single massive crane lift. Instead, it converted one continuous, unmovable obstacle into several independent, properly balanced lifting packages. Executing this heavy industrial dismantling required highly specialized physical labor. The composite nature of the minehunter presented unique mechanical resistance. Because the primary hull structure was wood and glass-reinforced plastic, the main cutting work could not be treated like ordinary steel shipbreaking. Hot work was limited and tightly controlled, while the dominant tools were mechanical. Operators used heavy-duty chainsaws and large reciprocating saws against the primary wooden and composite framing of the warship. Some underwater cutting was carried out with hydraulically driven tools, while localized metallic components were dealt with separately under strict safety control. The physical work on the slanted decks was incredibly grueling and highly precise. The crews had to cut blindly through thick composite laminates, dense wooden beams, and dense internal wiring bundles. The sheer thickness of the main wooden hull framing generated immense mechanical friction against the heavy steel saw blades. The cutting process produced massive amounts of sawdust that mixed constantly with the corrosive saltwater spray. The outer glass-reinforced plastic sheathing rapidly dulled the cutting chains, requiring constant equipment replacement and maintenance directly on the exposed weather decks. As the giant chainsaws bit deeply into the wooden hull, the tool operators had to continuously monitor the structural tension. A ship rests under immense internal stress. When major load-bearing timbers are violently severed, the surrounding framework shifts unpredictably. The cutting teams carefully sequence their deep vertical slices to prevent the massive sections from suddenly collapsing inward or violently springing apart under the uneven weight distribution. The systematic dismantling progressed methodically layer by layer. The salvage team successfully severed the entire rigid spine of the vessel. The heavy reciprocating saws ground completely through the transverse bulkheads, opening wide physical gaps between the adjacent structural compartments. The continuous structural envelope of the warship was completely eliminated. The engineers precisely divided the wooden hull into exactly 4 independent sections. Each isolated block now stood fully separated by clear physical air gaps. The blocks were cut, but how does a heavy lift crane approach them without dropping its own massive anchors onto the reef? The shattered wooden mass was now reduced to exactly 4 distinct, mathematically calculated industrial packages. The radical dismantling strategy worked flawlessly on the stranded deck. The heavy blocks are completely severed and ready for extraction. The blocks are cut, but how does a heavy lift crane approach them without dropping its own massive anchors onto the reef? The final extraction sequence demanded immense mechanical power paired with extreme physical precision. The 4 severed hull blocks were ready for removal, and each section weighed on the order of hundreds of tons, with several lifts described at roughly 250 tons. Lifting a load of this sheer magnitude requires an exceptionally large industrial crane ship. These massive deep-water construction vessels are inherently unstable when operating close to shallow hazards. The traditional stabilization method dictates deploying a massive spread of heavy steel anchors. A crane ship drops multiple huge anchors far out in a wide perimeter, dragging them deeply into the seabed until they bite. The ship then hauls tightly against these chains to lock its physical position perfectly still before initiating a heavy lift. On the Tubbataha Reef, this standard anchoring procedure was effectively off the table. Dropping massive steel hooks and dragging heavy mooring chain near the biological shelf could cause the exact environmental destruction the Salvage Command had sacrificed its own ship to avoid. The anchor chains could sweep through fragile coral heads as the crane ship shifted under the lifting loads. The operational boundary was uncompromising. The massive extraction vessel had to approach the hazard closely, hoist huge industrial weights off a shallow marine shelf, and maintain station without placing reef-damaging moorings on the surrounding sea floor. The operation deployed the Jascon 25, a heavy construction vessel with dynamic positioning capability. Instead of anchoring, the crane ship used computer-controlled thrusters tied to positional references, heading data, motion inputs, and environmental sensors. Those inputs drove continuous corrections against wind, current, and sea state. The vessel did not hover in perfect stillness. It remained inside a controlled operating envelope close enough for the crane to work without dropping reef-damaging hardware. The heavy lifting sequence commenced under careful load management. The crane operators slowly swung the massive, heavy-duty hook over the shattered wooden wreck. The salvage teams on the stranded sections manually connected the industrial rigging slings around the heavy wooden framing of the first block. As the winches took strain, the crane team and vessel crew managed the changing load while the dynamic positioning system maintained station inside its allowable limits. The physical extraction was incredibly precise. The crane drew the first section vertically off its jagged coral foundation, held the shattered wooden block suspended, then swung it clear of the sensitive marine park and lowered it onto a waiting barge. Section by section, the same lift logic removed the heavy blocks from the reef. The lifting sequence had solved the final physical barrier. The wreck was gone, but what is the final ledger of this unprecedented operation? For 73 days from the grounding to the final hull lift, a commissioned naval vessel occupied a highly protected biological sanctuary. Throughout that period, salvage teams worked to keep the heavy mechanical recovery from spreading damage beyond the wreck site. The primary hull removal reached its decisive milestone on March 30, 2013, when the final section of the shattered wooden hull was safely hoisted clear of the reef. With the visible mass of the warship gone, the heavy construction vessels, receiving barges, and fluid transfer systems began leaving the Sulu Sea while cleanup and assessment continued. Final inspections confirmed the central containment result. The wreck had been removed, the diesel fuel had not leaked, and no residual internal machinery was left behind to degrade in the shallow waters. The ledger was still not spotless. The grounding itself damaged more than 2,300 square meters of protected reef, and the United States later paid compensation to the Philippines for that damage. The real achievement was narrower. The recovery prevented the original injury from expanding into a wider salvage-caused disaster. The extraction of the ruined hull closed the most dangerous physical phase of the crisis. On day 73, the final section was gone from the reef. What remained was not a perfect return to untouched nature, but a damaged site freed from a wreck, ready for assessment, cleanup, and the slow work of biological recovery.